Chapter 5 is all about stereochemistry, which is the 3D structure of molecules. There's a lot of terminology at the start of Chapter 5, and eventually we'll start drawing structures and have a better understanding of how stereochemistry and stereoisomers are different from constitutional isomers and things that we already know. So to start out with, we need to talk a little bit about what isomers are. Isomers are only different compounds with the same molecular formula. And the kind that we've learned about already are constitutional isomers. Constitutional isomers, the definition of them is that they differ in the way atoms are connected. And that leads to different names of our compounds. They can have different functional groups. And they will have different physical properties. And they'll have different chemical properties. An example of that might be something like ethyl methyl ether versus propanol. Those are two constitutional isomers that are both C3H8O. Now we'll contrast that with stereoisomers. Stereoisomers differ only in the way atoms are oriented in space. They have the same connectivity. Now, what does that lead to? They have identical names except for some prefix, which we'll talk about in more detail later. They always have the same functional groups. They have all the same physical properties. And they have the same chemical properties, except, there's one exception, to other stereoisomers. An example of a stereoisomer would be an alcohol with the hydroxide coming out versus this alcohol with the hydroxide going back. All of the bonds are in the same places, carbon, 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 4 carbons in a row, and a hydroxide coming off the second carbon, or an alcohol coming off the second carbon. 4 carbons in a row with an alcohol coming off the second carbon. There's one hydrogen on that carbon, there's one hydrogen on this carbon. The only difference is that this hydroxide is coming out at you, and this hydroxide is going back into the plane. It only differs in three-dimensional aspects of where those groups are oriented in space, not in any kind of connectivity. And we call these differences in stereochemistry configurations. So these two isomers are different stereoisomers, and they have different configurations. Now I'll continue to introduce new topics for this chapter until we can put them all together. So the next really important topic is chirality. And the idea of chirality has to do with mirror images. So any object can have a mirror image. What's interesting in chemistry is whether or not the mirror images are superimposable. If they're superimposable, that means that they're identical. They're the exact same thing. If they're not superimposable, that means they're not identical. Somehow these two objects are different. A great example of how to see this is to look at your hands. Now, if you want to look at page 170 in the textbook, that would probably help because that will give you an image of what I'm describing. But if you take your hands and you place them out in front of you, you can hold them up thumb to thumb, and you can see that they're mirror images of each other if you hold them out parallel to one another. Then if you try to overlay them on top of each other, with both your palms facing down, what you find is one thumb is going to be on one side, one thumb is on the other side. They don't line up. Okay, so that's the idea of they're mirror images of each other, but they're not superimposable. Your two hands are not interchangeable. One is opposite of the other one. In chiral, all that means is non-superimposable mirror images. Okay, they're mirror images, but they're not the same. Now, an opposite idea to that might be something like socks. Most of the socks that we wear are mirror images of one another, but they would be superimposable. So if you switched your left sock with your right sock, it wouldn't make much difference for most people. So then the opposite of chiral is achiral. Achiral is a molecular object that is superimposable on its mirror image. Again, that means that those two mirror images are identical. So if that's what chirality is, how do we test for chirality? So the first thing that we'll do is we need to draw our molecule in 3D. Or simulate 3D. We need to draw its mirror image. Then we need to try to align all the atoms. And all the bonds. And when we do this, you're allowed to rotate the molecule any way you want. But you cannot break any bonds. This is also where some people would like to use a model set. So model sets can be helpful for this as well, for trying to understand chirality of molecules. In the end, if the two mirror images are superimposable, then they're the same molecule. And they're achiral. If they're not superimposable, then they're not the same molecule, and they're chiral.